Alright, so this is the first few slides are just a recap of what we did last time. Like I said, architectures can be compared on in a few different ways. One is in terms of the computational units that they have. The next is the clock frequency, the frequency of operation of the system, and then the bus bandwidth, how much data can you pump in or out of the system per unit time. Okay. So computational units, typically we are talking about some kind of an arithmetic and logic unit. Integer operations we assume are always present no matter what kind of hardware architecture we are looking at. Floating point coprocessors are very common in modern systems, but as we will see, there could be systems where you don't have floating point natively. Typically microcontrollers and low powered devices do not have floating point. Another example is custom hardware. Floating point typically ends up being much more expensive in terms of just the area and the power, etc., than integer operations. We'll understand that a little bit better when we actually look at floating point representations and arithmetic in detail later. Computational units, typically there are specialized multiply accumulate units that are often found, especially for signal processing applications. And in terms of the FPGAs, we come across a concept of something called a DSP slice. They are called DSP slices because the primary use of those slices is to implement multiply accumulate units. But in general, you can think of them as some hardware unit that is capable of doing multiplication. Clock frequency, what is the maximum speed at which a system can operate? It's typically determined by the complexity of the hardware, that is the critical path, which is in turn the longest combinational logic path through the gates that build up the circuit. The higher the clock frequency, more power is consumed in general, right? And part of that is related to the fact that when you are toggling the clock more often, the other signals are also going to be toggling at a rate proportional to the clock. That's the expectation, otherwise they are not really doing any useful work, right? And ultimately the power consumption or the energy consumed in any circuit comes down to how many times any given output of a gate switches from 0 to 1 or 1 to 0. Okay, the number of times that transition happens is pretty much proportional to the total energy that you are going to consume. You can do something called overclocking, which is basically operating at a higher voltage and therefore operating at a higher clock frequency than your system was nominally designed for. It has other problems because of course you can run at a higher clock frequency, but it means you are also running at a higher voltage, and this has a more than linear effect on the power consumption and can result in drastic increases in the power that your system is going to consume, which not only is bad from the overall power consumption point of view, it might also make it thermally unstable and it can actually destroy circuits if you are not careful about it. The bus bandwidth refers to how much data can be transferred into or out of the system per unit time, and it's usually done with multiple wires that are synchronized together to form parallel buses. Off-chip transfer is often better done using serial buses. USB, the universal serial bus, is a good example of that. Firewire, the Thunderbolt, all of those are different variants of how serial buses can really go to high speeds, much higher than what you would typically find on parallel buses. There are solid reasons behind that, which we will not get into as far as our course is concerned. One issue that comes is that typically when the moment you are going off chip, the capacitance that you have to deal with is much higher than if you were only trying to read or write from a memory block that was on chip, right? Capacitance at the end of the day is a physical quantity. It depends on the area of the metal plates or the wires that you are using to connect, the thickness of the wires, the length of the wires, all of those. So the moment you are going off chip, all of those numbers increase. They are much higher than what it would be inside a single chip. So capacitance is higher, delay increases, power consumption increases. In general, if you can do something by storing data on chip, you are probably better off than if you need to keep going off chip. Wide buses at the end of the day are always good in the sense that you can transfer more data per clock cycle, which translates into more data per second. But it's harder to synchronize wide buses. So they are used only in specific cases where you exactly want that high bandwidth, high throughput kind of communication.